Let's begin. Hi, my name is Shaashvat Sekhar, and this is a video about CPU architecture in the course EE224 Digital Circuits under Prof. Sachin Patkar in autumn 2024. I'm making this video as a part of some extra coursework. Let's move. So before we start talking about CPU architecture, let's first talk about the context and the motivation to build something like a CPU. And that starts with talking about the state of electrical engineering and computer science in the 1960s, or for convenience, what we have studied in digital circuits up till now, and to some extent what we have studied in our computer science courses up till now. Okay, so in the 1960s, the MOSFET was invented. A MOSFET was a voltage controlled current source, and MOSFETs could be used as switching devices and could be used to implement digital circuits. Now, the first kind of digital circuits that MOSFETs could implement are the combinatorial circuits. What do the combinatorial circuits do? The combinatorial circuits have outputs that are functions only of the current inputs to the circuit at that current time, as in it has no dependence on what the past state of the inputs were, only what the present states are. And MOSFETs can be used to implement combinatorial circuits. Now, the second kind of circuit that MOSFETs can be used to implement are the sequential circuits. What are sequential circuits is? Sequential circuits use the Boolean gates and design them and construct a complex gate in such a way that it can store or rather hold values. And how that is used is we create using a clock, which is like a pulse with a certain fixed frequency, high for a fixed time, then low, then high, then low, then high, then low. What it essentially does is that it can hold a fixed value for a clock interval, and at an edge of the clock, say at the rising edge or at the falling edge, it can update its values. So what a sequential circuit does is that using a clock and using these registers that are used to store values and that are implemented in MOSFETs using master slave latches, what we can essentially do is that we can have a circuit where the outputs are a function of both the current state, which are values stored in our registers or the values held by the latches, and the function of that as well as the inputs to the system at that current time. Now, what we have learned about sequential circuits is that they can be used to implement FSMs, Moore FSMs, where the output is only a function of the current state, and Mealy FSMs, where the output is a function of both the current state and the current inputs to the system. So a small recap is what we have learned from electrical engineering, and also to some extent what would have been the progress, I assume, in the 1960s, is you realize that digital circuits can be used to implement combinatorial circuits that are only a function of the current input, and clock sequential circuits that are a function of the current state of the registers and a function of the inputs to the system at that time. And what it also does is that combinatorial circuits also have a logic to update the states. So essentially, based on what the current inputs are and what the current state is, it can be used to update the states. And basically what we realize is combinatorial circuits and sequential circuits can be used to implement FSMs. Now, what are FSMs? Finite state machines are an abstract machine that it can be in exactly one of a finite state of any time at any given time. And it says that the finite state machine can change from a state to any other state in response to some inputs given to the finite state machine. So this is what we've done in EE so far, electrical engineering so far. Now let's take a look at CS for a second. So a long while back, theoretical computer scientists, when everything wasn't necessarily implementable as well, came out with the concept of programs. And they define programs as an ordered list of tasks that are used to follow out or carry out a certain task. An ordered list of instructions that are followed to carry out a certain specific task. Now this just seems like a very simple definition that okay, you do some instructions and follow them through, and you can you can carry out a certain task. Now, that seems like a very trivial statement. So why did computer scientists care about programs, and why do we care about programs? Is that they're incredibly powerful constructs. Programs with certain capabilities like the ability to loop, the ability to do conditional execution, the ability to do assignment, some base with just some basic operations can do a very powerful list of computations and can do a very powerful list of tasks. A very so rather, I think the list is they are very powerful constructs that can be used to carry out a very versatile range of tasks, rather than saying that the tasks that they carry out themselves are powerful. Anyways, that's just a diversion. So programs are powerful constructs that can be used to carry out a wide versatile range of tasks. Now let's take a few examples. Here is a program that can find the nth Fibonacci number. Now what is the Fibonacci series? The series starts with 0, moves to 1, and every subsequent value is the sum of the two values that preceded. So the third Fibonacci number is 1, the fourth is 2, the fifth is 3, the sixth is 5, and so on. Now say we want to implement a program that can find the nth Fibonacci number. So we, as you can see, how what this program does is that if n is 1, then we just output 0. If n is 2, then we just output 1. However, if n is greater than that, we can run a loop that iteratively keeps adding the last two numbers to find out the every subsequent number, and then it can output that. An example of a sort algorithm. Here is an algorithm that does conditional execution of flipping of values stored in an ordered list of stored in an array or an ordered list of registers, and based on just checking if two next to based on just looping through the entire array and just checking if the two consecutive values are greater than if the one value is greater than the other, and then just swapping the values in a case, we can basically carry out sorting of n. We can carry out the sorting of n registers, n ordered registers, or an n length array. Then here is a famous program called the Newton-Raphson program, which can approximate the root of any function to any specified degree of precision, given that this function has certain properties, I think to do with the convexity, convectivity, but I will not go there for now. So what the program does is that it iteratively finds a better approximation of the root on and on and on until we are at a satisfactory level. And it's used as it's a very simple operation that basically has a constant loop that keeps making the approximation closer and closer and closer, and the loop that breaks when the approximation is close enough. Now we've talked about complex programs, right? Now another realization about programs is that complex statements can be written as multiple simple statements. For example, what we did in the Fibonacci, a statement that is give me the n Fibonacci number is as precise a statement as is actually can be considered a program, because it is a very well defined and it is a list of instructions. It's a single instruction, but a single can be considered a list. However, that is not very meaningful to do, because it is not it's something that is very abstract. However, breaking it down into set the first Fibonacci number is this, set the second one like this, then if you want to send the third, fourth, fifth, and so on, write a for loop that calculates it. That's a much simpler way of executing such a thing in a way that it is still well defined and it is convenient to interpret and convenient to execute. Now another example of this is, say we want to add numbers. Now adding numbers, we can add any number of numbers, because addition is distributed, like a plus b plus c is equal to a plus b plus c, and so on. Now writing such complex statements, like in this case what I've shown on the slides is a0 plus a1 plus a2 plus a3 a4 a5 and so on, is a very complex statement. And in most cases complex statements like this can be broken down, where we basically create a variable called sum and keep adding the next value of ai to sum. So first take sum, then add a0 to it and save it to sum, then take a2 and save it to the newer value of sum, then take a3 and save it to the updated value of sum, and so on until you add all the a9. Or instead of writing in a loop, you can just hard write it, that sum is equal to a0, then sum is equal to sum plus a1, then sum is equal to sum plus a2, and so on. Now what we basically realize that programs do is that they carry out a series of instructions that each operates on some stored values. That is, the instruction that we are giving considers some stored values, considers the value of considers some stored values and keeps updating them at every step. Now let's draw an analogy here, that if we consider the instructions as inputs, if we consider the store values as states, and if we consider the operation as next state logic, as in from this state how do I go to the next state. For example, say it's add 2 to the value of this register, or add 2 to the value of this state. What that would be is that the stored value would be what the current value is. Say if it was something like 5, the operation would be, you know what, we want to add 2 to it, and so our next state has to be whatever the current state is plus 2, and that would be 7. So our next state logic would output a 7, and the instruction would be something that just says that writes the circuit in such a way that the next state is 7. Now drawing this analogy makes us realize that programs can be implemented on an FSM by giving the program a series of instructions. As in an FSM, as in we have an FSM that has some next state logic and has some inputs, and giving the instructions as inputs, we can carry out any program with that. We can carry out a wide set of programs on this FSM. So if you look at what we've done so far, in EE we've realized that MOSFETs can implement FSMs, and in CS we've realized that we can implement and MOSFETs can implement FSMs, and MOSFETs can implement digital circuits. So let's focus on it being a digital circuit. Digital circuits can implement FSMs, and from CS we realized that programs can be implemented on an FSM, and programs can be written in terms of simple statements. So what this means is that what this basically tells us is that we can somehow write a certain FSM, we can design a certain FSM that can carry out some set of programmable instructions that are conducive to a certain set of inputs, and can carry out a program that acknowledges those inputs. So the question naturally arises is, how do we build such a programmable FSM? How do we feed a list of instructions to this FSM? Because if you want to operate at a very high frequency, if you want to carry out the program very fast, we cannot manually do such a thing. So we would prefer if we were able to feed a list of instructions to this FSM. And the third question is, how do we implement it on a digital circuit? And what is the motivation to do this is, programs are incredibly versatile and incredibly powerful, and if we are able to do such a thing, then we can carry out a wide range of operations, a wide range of activity, a wide range of calculations on a digital circuit, on a MOSFET circuit. So this basically lays down the motivation of why we want to build a CPU, of why we want to build a CPU, and that we have the abilities to build a CPU given our knowledge of what's in theoretical CS, and given our knowledge of basics of digital circuits and basics of what technologies we have, that is the MOSFET. So now let's go on to the next step, is let's talk about how do we design a CPU to do such a thing. Let's talk about CPU architecture now. So von Neumann proposed the idea of a fetch execute cycle. Basically, the fetch execute cycle was a template for how to design a CPU. How it works is that fetch execute decode cycle. How it works is that first the CPU would fetch the address of the next instruction from the program counter. The program counter is something that holds the address of the next program. It sends this address to the program memory, which then returns the instruction that is stored in that address. Hence it's called fetch, rather fetching the instruction that is to be executed. So then given the instruction that is fetched, the CPU decodes the instruction. That is, the instruction is encoded in a particular format to save space on storing, to store it in minimal bits, to store it in a particular format. However, while implementing the logic itself, it is easier to decode it to instructions themselves, and hence the next step of the process is decoding the instructions to a more legible mapping. And in the case of the CPU that is used by in the 281, they use one-hot encoding, which is basically that based on whichever instruction there is, the decoder gives out a one-hot output of which instruction to carry out. that makes writing the logic for the controller much easier, because then the focus is on sending control signals based on which instruction is there, and not based on how the instruction itself is encoded. The third part of the von Neumann fetch execute cycle is to execute the instruction. How this works is that the instruction is executed, that the instruction is received by the control gives signals to the different parts of the CPU as to how to operate, whether some bits are to be read, some bits are to be written, some bits are to be transferred, which operation by the ALU is meant to be carried out, and that is the execute process. Once the execute is done, there's a fourth process, which is an optional, which is a store update values, which means that the updated values that are generated are either written to some register or are written to the memory itself, the data memory. This is in a sense the fetch execute cycle. How it's implemented on the CPU is a bit more complex than that. Let me go into detail. So first you have the program counter that has the address of the the next instruction to be executed. The program counter sends this instruction to the code memory. The code memory sends the instruction that is stored in that address out to the opcode detector and to the ALU. Now the opcode decoder creates one hot lines of which instruction to carry out, and the control, based on those one hot lines, sends bits to different parts of the ALU registers and muxes as to what is the logic for writing, reading registers, memory values, and also which operation to carry out, and also how to update the PC update, and also how to update the program counter. And this is generally how the fetch execute cycle works. Then at the next clock cycle, the value of the program counter is updated based on what the update logic was, and that sends the new instruction to the code memory, and that sends the new instructions to the decoder, etc., and thereby the cycle repeats all over again. Now this begs the question, so the program counter is storing the address of an instruction and of the next instruction to execute, and there is some logic as to how to update the program counter, and how to update the address of which program to be executed. Now that begs the question is, how are these programs being stored that the program counter knows which instruction to carry out and how? And the way it's understood is that, and this is a elegant piece of design where the instructions are all sequential. Like there's instruction 0, instruction 1, instruction 2, instruction 3, and so on, all the way up till as many instructions are needed, and they are stored serially in the, say, if an instruction requires 2 bytes, then the first instruction is stored in 0th, then the second instruction is stored in the second and the third bits, then the third instruction is stored in the 5th and the 6th bits, and so on. And essentially what happens is that by default the program counter knows that the next instruction that I have to carry out is always the instruction after it. So by default, the program counter knows that whatever is my current address, I just have to go to the address that is shifted by the length of the instruction. So as in, if the current address is 4, what that means is that if the length of an instruction is 2 bytes, then it has to go to 6. If the length of the instruction is 4 bytes, it has to go to 8. Now this is a very elegant process, and it works for all code that has to be run sequentially, as in there is a single process to follow, and there are no branching, there is no looping. However, in the case of branching and looping, this code of just going to the next instruction doesn't necessarily work. Now to handle that, 2 separate new instructions are created, and the way they essentially work is that rather than going to the next address by default, if the instruction go to is run, it goes to a specific address, which is and the way it's generally defined is go to the next address minus some shift. And this can be used to implement loops. Basically, once you reach an address, you go back to an address that was before the current address, and thereby you again go back, then come down, then go back, then come down. Thereby you can run a loop. Now in the case of if else, an instruction can be, in the case of implementing an if else statement, an instruction can be written which basically says that if so and so condition, then go to this address, or if so and so is condition doesn't hold, then go to some other address. And basically what that implements is that and then once it goes to that address, then again the logic starts of do the next instruction. And what that basically means is that you can have an if else loop, if else condition, and by default the instruction keeps going down. So you can skip instructions using this if else kind of go to next program counter. How this is implemented is that the PC update logic by default will add some X bits to the program counter. However, in the case that we need to do some special operation that is not just go to the next counter, in that case the program counter is updated with a different value, that is the value that we would like to go to, or the value that instead of just by default going to the next instruction, you go to a very specific instruction. And it achieves this by having a PC update logic that takes a signal from the controller that decides, okay, do you want to go to this do you want to go by default to the next instruction, or do you want to go to a specific instruction? And the PC update logic, which takes an input of the current state of the program counter and some input from the instruction go to instruction as to which is the instruction to go to. And this is essentially how programs are stored. And using this format of storing and updating programs, essentially any program can be run, because we've established that we can do conditionals, execution, branching, loops, and that more or less covers everything. And we can also do go to a statement, like say if we reach somewhere, go there, go here, go there, and hence we can very easily run any program using this program counter logic update. Now let's talk about the second part of the CPU, that is decoding. So now we know that the program counter has sent the address of the next instruction and has fetched it. It has fetched it from the program memory, and now it begs the question, the program memory has the instruction. Now the CPU is required to decode this instruction to execute it. So here we must first take pause and understand that the CPU is designed around the instruction set. And what this means is that the design of the CPU is done with the instruction set in mind. As in, we need a CPU that can do a certain list of operations and a certain list of programs, and given that we design an instruction set, and now the work to be done is to design a CPU that can carry out all the instructions in this instruction set, and thereby able to implement any program that can be implemented using this instruction set. Now, instructions themselves are stored and encoded and stored for the convenience of reducing the number of bits they're required to store in, for the convenience of having a certain format. They're encoded and stored. And what that means is that in order to make the control logic easier, in order to make the control logic more convenient, they require decoding. In the case of the 281 CPU, the opcode detector takes the 8 high bits from the code memory, that refers to the instruction, and it sends 27 one-hot lines to control. The 27 one-hot lines are each of which instruction to carry out, and only one out of 27 is on, corresponding to which instruction is to be carried out next. This is decoding. Now, after the decoding process is done, what we have reached is that the CPU has knowledge of which instruction is to be carried out, and it has some extra information about maybe some register addresses, some updates, some values, and now it takes these values and carries out the function, carries out the execution in the ALU. So let's talk about that now. Now, a few general instructions that are to be carried out are add, subtract, and or not, compare, branch if, go to, read from, write to, shift bits. Now, each instruction requires different functioning of CPU components. And so, how a CPU is designed is that there are control lines sent to all components that ensures that the execution happens as per the instruction that is provided. These control lines basically tell each individual subcomponent of the CPU that given that I have this instruction, I need to do A, B, and C, and not C, D, E, F, G. And or else I have to do these things and not those things. I have to write here, read from here, write there, carry out this operation, update the program counter like this, etc. Now the issue that arises with execution and instructions is that the more instructions that we want and the more complex instructions that we want, the more the delay is there in the ALU and the control logic circuits, because each of these elements, each of these circuit elements have some kind of propagation delay, and the longer and longer we make our instruction sets and the more complex we make our instruction sets, the slower the clock is and slower the operation is. Why we want to speed it up? Although one can argue that say if you had now an example like this is, say we have adding if you add 3 numbers together, we set an instruction called y is equal to a plus b plus c, as opposed to having a minimal instruction where you set y is equal to a, then do y is equal to y plus b, then do y is equal to y plus c. What would happen is that the clock has to run at a single frequency for every single instruction. What that means is that the limiting instruction, the slowest instruction, slows the running of every other instruction. So it is of pertinence, it is of importance to have each and every instruction be of minimal time, and that ensures that the average case and the most commonly used cases are running at fast pace, and the few cases that are not running at fast pace, it is worth increasing their time, so as given that because the average time of execution will decrease, because the longer ones are generally slightly rarer cases. So the conclusion here is that the ALU becomes slower when we have larger instruction sets. So we have an incentive to keep our instruction sets minimal. Now the other time optimization that we need to do is that if you look at the memory that we have in these circuits, the memory can only read and write from one address at a time. It means that there is only one input of address to the memory and a write enable signal, which means that it can only read and write one address, and that address is the same. However, in the case of a lot of computing, we require operations to be done on two addresses, on two sets of data. Like, for example, an addition operation, or a subtraction operation, or a bitwise AND operation. And the second problem the memory has is that the memory is slow. So how these problems are solved is that the CPU contains an internal register bank. This register bank contains multiple registers, and it has at least two lines that can be read out from the register, which means that carrying out 2-bit operations, carrying out two data operations on 2-bit two words of data becomes a lot easier, and it also becomes a lot quicker. Now in this case, say we wanted to add two values from the memory, how that would work is that we first load one of the values onto one register, then we load a second value onto a different register, then we add the two registers together, and then we write the sum of the two registers back to the another piece of memory. This is essentially how working with memory and registers works. Now let's talk about some of the assembly instructions on the i281 CPU. So as you can see here, this is a like somewhat close to minimal assembly instructions, and what it contains is let me talk about this. NOOP is no operation. Input C is input into code memory, which means that which means you input a value into the code memory. Input into the code memory, then offset means you input into, if you know, say we have arrays, we want to store arrays in the code memory, and array is referenced by the pointer to the initial value plus an offset. So inputting CF inputs into the code memory with an offset. Then if you want to input into the data memory, we input D works, then input DF inputs into the data memory with an offset, then moves the contents of registers from one to another. Load I loads an immediate pointer, then adds two registers. Like I mentioned here, two input operations are carried out using registers, not memory addresses. Then there's subtracting, loading, storing, shifting, jumping, branching, and comparing. And all these achieve is using this minimal set of assembly instructions, we can actually carry out a versatile set of programs. Now this is the case of this specific slide refers to the i281 assembly instruction that is designed for the i281 CPU. However, a more general CPU would be a more general CPU architecture is that of MIPS. Let me just talk about MIPS for a second. MIPS is basically the default assembly language for a wide set of computers, and they also have a minimal set of instructions with some specific encoding with a known value of registers and addresses and address lengths, and that makes writing any code onto MIPS by default able to run on a lot of CPUs. Anyways, I digress. Now that I've explained that registers are used for quick data access and writing and the memory is slow, let's go back into how the controls work. So we talked about the opcode detector, the opcode decoder, which decodes the code, and sends it to the control using one-hot signals. Now these one-hot signals send different lines of control to different parts of the CPU to basically determine how an instruction is carried out. Now let me talk about it. So the first set of lines, C1, C2, just a second. Okay, fine. I don't have to go in order. Okay, so take a look at C8, C9, C10 that go to the registers, and C4, C5, C6, C7. Now C4, C5 is a mux which determines which register from ABCD is read out into the first register. C6, C7 determine which is the second register we want to read out from the register bank. C8, C9, C10, C8 and C9 determine which is a register we may want to write to, and C10 sets whether we want to write or not. So if C10 is high, then a register is written. If C10 is low, then a register is not. These are all control signals. Now C12, C13 are control signals to the ALU, which determine which function the ALU needs to carry out. And then C14, C15, C11 are flags or muxes, and C11 determines whether the second input to the ALU is from the register bank or it's from the code itself. And how that works is, some of the operations require a adding two registers. However, in the case of a default add, say we want to add one, like a increment, add I, which is a very generic case, there is the convenient solution is to write a instruction that stores add I and stores the value of one register we want to read from and the register we want to write to, and it also stores the values we want to add, so we don't necessarily need to read two registers. So that's what C11 carries out. Now C15 determines what is the outputting, how is the outputting of it. Then the other control lines are for the memory. If you look at C17, it determines whether the memory is to be written to or not, and the four bit lines from the code determine into the data memory determine which is the memory location you want to write to. Now take a look at C2 and C3. These determine whether we want to update the program logic. So it determines, do we update the program logic by one, the standard increment, or do we need to do a separate increment in the case of a jump. This is what program, or if you want to jump to a specific point, if you want to jump to a pointer, this is what the control signals to the program logic does. And essentially this is essentially using these control signals, given an instruction, the person designing a CPU has to determine which of these instructions have to be set high, set low, to carry out the proper functioning of the instruction. Now take a look at the instructions again. Although I've gone over this, I'm just going to go over it again. Take a look at, say, add, for example. Okay, now let's look at the controls for add. So what add does is that it sets 1 to program counter write enable. What that means is that we want to write the program counter enable to 1. Then add also sets the register port 0 to x1 x0, and it sets the other registers to y1 y0 and x1 x0, and that determines which two registers have to be added and where does the result of this addition write to. And that is essentially how the instruction is encoded to be read. So as you can see in the controls, the 8 highest significant bits of the code memory are sent to the decoder and the control, because they determine both which instruction is to be carried out and what addresses are to be carried out, what addresses are the instruction to be carried out from. However, the 8 low are not used for that. The 8 low are used for writing values of addresses of increments or decrements. They're actually used more like variable storage. Now let's look at what happens inside the decoder. So the decoder takes I15 down to I8, which are the 8 most significant bits of the instruction, and they decode the output to determine which instruction is to be carried out. Of the EE224 CPU carrying out bubble sort. As you can see, the instructions are loaded in the program register on the left up till 110010, and the instructions are encoded as per load. First load the values and then compare and sorting. While I'm not going to go into the full depth of it, you can see how the control signals and the data path is flowing. Here we go. Let's see. Run it. Slow speed. As you can see, it starts with basically loading the values of the memory onto registers, comparing the values of the registers and then swapping accordingly. Then moving on to the next register, loading the values, swapping, loading, swapping, loading, swapping. until it reaches the end. Then it starts on the second, and so on. How bubble sort works, as you can see. So it carries out the simple procedure of load, load, compare, and in the case of if and else and looping, we use the branch if and the go to simplify our it's not simplify to write our branching and looping. So I'm just going to skip forward a bit. As you can see here now, this has been able to sort through bubble sort the values of from 0 to 7. It has been able to sort the 7 values of the array. This is an example of bubble sort carried out by the i298 i281 CPU. Now there's a few more, but let's take a look at this. If not equal to, what this does is that it loads the value of x onto register A, then it loads the value of y onto register B. It compares A and B, and it branches to the end if the comparison is different. So let's take a look at it. Go to CPU, run. So load, then branch. Now since there, what it has basically done is, since A and B are not equal, it has written the value of A to register 3. If in the case that they were equal, it was simply skipped to end. Examples of writing code in MIPS in assembly, that is in instruction sets. So let's take a look at this. The first code, what this does is, if B is greater than A, then set C to B in MIPS. How this works is that, first is that the SLT command sets $T3 to 1 if true, if A is less than B, and sets it to 0 otherwise. Then the BQ branches if T is 0, and it branches straight to the end. That means it never sets C is equal to B. If T is not 0, then the branch doesn't occur. Then it moves to the next instruction, which is moving T1 to T2, and that sets C to the value that is set in B. Now let's take another example. Let's talk about how this works. What this does is, basically, you have code, you have loop, which is a pointer where you want to go to, and you have code that adds. Firstly, you have code that sets the initial values to of your registers to values that we want. So it sets $T0 to 1, which is the loop counter. It sets sum to 0, which is $T1, and it says $T2 as the upper limit of our for loop to 10. And how it works is that, first it executes loop as it's a blank execution, then it moves to the next, which is add $T1, add a $T1, $T1, $T0, which basically adds to T1 the value of T1 plus T0, which is basically, it does sum plus I and adds it to and sets it to sum. Then what it does is that it updates the value of I by using the add I command. As we talked about, the add I is not a 2-register operation. It's a single register operation that has one register to write to, one register to read from, and values that come in the least significant bits of the instruction. Then the BLE is a branch that goes to loop if I is less than equal to 10. It compares t naught and it compares t2, and if I is less than equal to t2, then it goes back to loop. So it's like a go to from down here up here and again runs the loop. However, if that does not happen, then it just go to the next instruction, which is an end. Okay. Hi. Thank you for watching. I hope this video has helped you understand CPU architecture in great clarity.